Okay, last class we have been commenting further about vortex induced instability. Today, I will just bring one more aspect of description of this instability by using what is called as proper orthogonal decomposition. This is a specific technique which was brought into dynamical system studies pretty early, but which was only exploited much later. So, we will talk about some of these issues. What we understand by vortex induced instability is essentially written out here, that how initially the energy is transferred from the equilibrium flow to the disturbance field. That is the main issue. If we can predict that, we have predicted the primary instability, and we know once primary instability is triggered, that immediately brings in its wake secondary and tertiary instabilities that leads to eventual bypass transition. This is what we called as a bypass transition. So, during the later stages of bypass transition, you do actually notice large coherent vortices formed, which also are something similar to what one sees in fully developed turbulent flow. In this context of vortex induced instability and creation of coherent vortices inside the shear layer, we should recognize the early seminal contribution by Kosambi in 1943. He wrote a path breaking paper which remained largely ignored for a long time. The idea was basically to look at a dynamical system, but whose dynamics is determined by stochasticity. Stochasticity means it is a time dependent probabilistic event, right. So, if such a thing happens, how do you understand the dynamics of it? This is what Kosambi thought about, and he said that let us try to look at the dynamics of the system and try to project it in a deterministic basis. So, this is rather important. So, it is basically a projection of a stochastic system onto some deterministic basis functions, and these deterministic basis functions are orthogonal, and they are basically denumerably infinite. So, if you are looking at a truly a continuum system, you will have a very large number of them. But then Kosambi suggested that you basically look at such a system, but focus upon the energy content of each of these modes, and you decide upon yourself that you want to describe, let us say, the first 80% of the energy or first 99% of the energy, and then you would see this number of modes required to describe that quantum of energy is not necessarily infinite, they are finite in number. So, that was the catch, and this was seized upon by Professor Lumley, who have been investigating on application of this idea into fluid mechanics for quite some time. And there are the early efforts given in this monograph by Holmes, Lumley and Barkus titled Dynamical Systems. You can take a look. Then came another breakthrough, which was a practical method of computing this proper orthogonal decomposition. This was also done by Professor Syrovich of Cornell, and it is called the method of snapshots. This was a major breakthrough, you can say, which was proposed by Professor Syrovich in 3-part paper, which actually revolutionized fluid dynamics. Even today, we keep using POD for a great many of our investigations, and there are lots of new insights that have been really been introduced by us in terms of explaining fluid dynamics. For example, for vortex induced instability, we have shown it in this fast track paper in JFM 2003, and there was this conference come a journal paper in 2004, where we showed how we can use POD for bypass transition and try to capture those coherent vortices and characterize them. And as I told you, in these we have not only used the method of snapshot by Sarovich, we also used something akin to singular value decomposition. In linear algebra, you may have heard of singular value decomposition techniques. So, this is essentially used. The issue about this local analysis method, it's very robust. Suppose if I take a domain, here and then split it into two, and then I do POD on this path and POD on this part by using this orthogonal collocation method, Lang's collocation method. What we found that this method as compared to method of snapshot, this is quite powerful too. And what we could do is we could get some picture here, let us say a structure like this, and we did the analysis separately on this part of the domain, and then we saw that there is a virtually seamless matching of the two. So, this is a very powerful method. Unfortunately, though, it requires a tremendous amount of work, whereas this method of snapshots require very fewer number of snapshots, and you can do those calculations better. But nonetheless, they produce different quality of results, and you can understand that this kind of thing that we are talking about, it is a technique of signal processing. So, whether you want to talk about visual signal or audio signal, you can do it. In fact, in a commercial entertainment industry, this kind of POD kind of technique is routinely exploited in compacting data. You can understand that if I take the full dynamical system, the signal may be given by, let us say, 100 megabytes of data. And if I see that 99% of the energy is pretty well predicted by, let us say, 1% of this data, that so be it, right? That is a huge saving. So, these are some of the techniques also used as a data mining technique, people use it, but nonetheless we will not talk about that in great detail. Let us look at what we can do in studying vortex induced instability. What we do is basically we take the time series. So, if this is the time and we have some physical function, say f, and then we look at intervals of 10. And if we look at this time span of 10 and then just simply take 21 frames. So, these are those snapshots we are talking about. So, each of the frames are constituent of the method of snapshots. Okay. So, we are basically taking 21 snapshots over a time interval, non-dimensional time interval of 10, and then performing a POD. Okay. So, that is what it is. So, while this SVD or this Lang's collocation method gets you the spatial eigenvalues, and those require handling a very large number of size of matrices, whereas method of snapshots basically takes temporal series, right. That is what we are talking about. We are talking about 21 frames in the time frame of 10, and then perform the proper orthogonal decomposition technique. And once you do that, you can get the eigenvalues. If you are looking at the disturbance velocity field, then those eigenvalues represent kinetic energy of the disturbance field. If you are looking at the disturbance vorticity, then you are looking at the disturbance entropy, right. So, we actually can take both these routes. However, we realize that vorticity dynamics is more central in understanding fluid dynamics. So, we basically most of the time look for POD analysis for the disturbance vorticity field. Okay. And what we found is the eigenvalues and the eigenfunctions are as given here. For this simple problem of vortex induced instability, so we have this domain, and this is where the vortices are vortex is migrating. We can basically just simply look at how the flow is evolving. What you notice that when the primary instability has not started vigorously, like the time interval between 40 and 50, then you look at the way these are the ways the energy cumulatively increases, right. So, this first mode may account for almost 80%. The second mode accounts for here, it could be about, say, about another well, 5 and 6, about 0.11, 11% of energy second mode carries. So, first mode itself carries about 81%, then it is about 91, 92, then the third one takes you about 95.5, the fourth one takes you up to here, and this is a dotted line which is indicative of 99% of energy. So, although we are talking about a physical domain of having very large number of modes, method of snapshots reduces those thing by converting it into in terms of only 21 modes. The number of frames determines the number of modes. So, you understand why I emphasize on method of snapshots by Sarovich. This is that instead of looking at spatial eigenmodes of very large dimension, we are looking at a very few number of snapshots, and we get this. We will later on, time permitting, talk about most recent efforts in our lab, where we use much more accurate POD analysis and the kind of instability scenarios that we have seen in various external and internal flows is amazing. But nonetheless, you notice that here 99% of energy is given by first 5 modes during 40 to 50. The moment your primary instability starts and vortex induced instability occurs, then you see what happens. Then you see that to reach that 99%, we virtually exhaust all the 21 modes that we have, maybe 16 to 17, that kind of a difference. So, this are given at various time intervals of 40 to 50, the second data set is 50 to 60, and the third data set is 60 to 70. And what we can do is we can actually compare, let us say, the eigenmodes, eigenvectors at 2 time intervals. These two are eigenvectors 1 and 2 during time interval 50 to 60, and these are the same 2 eigenvectors, but now during the time interval of 70 to 80. Well, direct comparison will tell you what is really happening. This is about the incipient stage. You can always see this multi-layered disturbance vorticity structure, but cellular structure have started forming. And once they develop in time, you can see that each one of them actually creates those vertical eruptions that we are talking about. So, basically not a bad deal. You take a real true time dependent flow field, you do the numerical solution, now you do the POD, and you get a glimpse of what is happening. And you understand that this is a fairly decent tool to use. Why? Because you are not making any assumption, you are actually getting the nonlinear solutions and analyzing them. So, basically accurate solution of Navier-Stokes equation plus its proper orthogonal decomposition hands us down a very powerful technique of studying nonlinear instabilities. See, in doing this, getting these results, we have not done any approximation whatsoever. it is almost a concurrent development where we develop that energy based receptivity theory. We have shown in the previous couple of lectures that there also we did not require any assumptions of parallelism or linearization, etc. Directly using the Navier-Stokes solution, we could find out how the forcing is created for the disturbance energy, and that was that. And today we are giving you a complementary picture that you can look at POD and you can make use of this. Well, there are much more such pictures available in our 2003 paper, so you can take a look at them. Although here I have written on the y axis as energy content, it is not truly so, it is entropy actually, because we are working with disturbance vorticity, and on this side we have number of modes that is given there. Okay, so I think this was that I wanted to tell you about POD. So how do we talk about this? So basically what we do is we solve for the vorticity. So if I call that as the total quantity, that is nothing but omega mean plus say omega disturbance. I am not writing epsilon, but that is understood that it may or may not be a lower order quantity, but at the initial stage it could be. Now what you do, you get this, and if you recall while doing that energy based receptivity theory also, we talked about an equilibrium flow that could be the flow before the instabilities start occurring. So this is kind of predicted, right? So maybe in this case we would have taken at t equal to 20 as the equilibrium solution. So if I have this, then it's rather easy. So omega d at any time, I could write it as omega total at that time minus the equilibrium solution. And that equilibrium solution, as I was saying, it could be the omega total itself at a earlier time, maybe at t equal to 20. Okay. For this particular case that we have shown here, it is like this. So what happens is at each and every time I am getting this disturbance vorticity, then what I could do is I could create a correlation matrix, which I whose elements I could call as R I j. So I and j index refers to different time instants, and that I will be talking about, say, omega I at, so this is omega disturbance quantity at ith time frame for some x vector. I will rather write it as Ti. Okay. So that is what it is, and then multiply by omega d this at Tj, and then I perform the integral over all the collocation points. So in this case we are doing a two-dimensional calculation, so we will be integrating over the whole domain. So right, so this is this. So once I have this Rij matrix, then I can calculate Rij times, say, some eigenvector is nothing but lambda times x. So once you actually compose this Rij matrix, you just simply have to calculate its eigenvalue and eigenvector, and you know that there are many ways of doing it, and that is what we are talking about here as the eigenvalues. So those eigenvalues indicate the total entropy contained in specified number of leading eigenmodes, and if I look at a fractional entropy content, basically I add up lambda I divided by sum of lambda I, that gives me a fractional content. Okay, that's what we are talking about. We take the partial sum over leading eigenvalues divided by the total sum. So that's how we define. And one notices that largest eigenvalues is well separated from other eigenvalues, also up to until about t equal to 50, 5 eigenmodes more or less capture 99% of the energy, right, total disturbance entropy. And the number increases to 14 during t equal to 80 to 90. So that's this. This POD analysis is also given alternative names. People talk about reduced order modeling. Reduced order modeling, because instead of looking at an infinite dimension system, you are basically talking about, say, in this case, say 14 modes. That idea is the following, that if I could reduce the number of bases which defines this dynamical system quite adequately, then there is a possibility that I could change the governing partial differential equation into a set of coupled ordinary differential equation. The number of those ordinary differential equations happens to be low. So we may be talking about evolution equation of POD amplitude. So basically what we are talking about, I think we'll come back to more detail of POD later, but let's just keep our discussion today in a qualitative plane. Basically we show that these eigenmodes consist of a time dependent amplitude and a space dependent path, right. So these Rij's are obtained from the space dependent path, and this amplitude are the time dependent path. Those evolution equation I am talking about in reduced order models are those dynamical equations for those amplitudes. You can just take this representation of space time separation, put it in the Navier-Stokes equation, make appropriate modifications or manipulations. You hope to get those dynamical system model for those time dependent amplitudes, and this amplitudes that we are talking about here are only 14 of them. So this is what was originally proposed. We have taken it to a different level because we consider that we have the solution correctly available with us. We have this available all the time. So if I now get the spatial modes, I can actually, since omega total is written as a summation of let us say a time dependent function and the eigenfunction here, which is a function of let us say x and y, and k goes from 1 to n, then what we are talking about, since the POD analysis helps us getting this spatial dependent functions like what we plotted in the previous transparency. In the previous slide we did show these are those basically phi of x y, right. Here we are showing phi at different time intervals. So this is the phi 1, this is phi 2 during t equal to 50 to 60, and this is basically a phi 1 and phi 2 during t equal to 70 to 8. So what exactly we are doing? We are actually taking the data over a finite time interval and saying that during that time interval the first mode on an average looks like this. So this is a statistical depiction, right. These are not qualitative, quantitative, deterministic model of the functions, because the system is varying. So we are projecting a kind of a average value. Now once we do that, so we have this, we can easily obtain it. Why and how? Because these modes are orthogonal. So we can use the orthogonal property, and we can actually, from the accurate simulation, we can calculate how this A varies with t. This is the unique approach that we have chosen. We have faith in our direct simulation result. So we do this, And in doing so, we have come out over the last 2-3 years some fascinating pictures of how these things are obtained as a function of time directly from DNS result. However, originally Kosambi, Lumley and all, they were thinking of basically getting some dynamical system description of these modes, and this could be some function which could be functions of all a1, a2 up to say an. We do not know, and that they tried to obtain it from the Navier-Stokes equation. And in trying to obtain it from the Navier-Stokes equation, a lot of limiting assumptions have gone in, and in the process people have lost track of how good is this evolution equation is. But if you look at the way that we are talking about here, this is entirely different. We know this exactly. We have a very good description of phi, then we can get ak as a function of time, and we can plot it, and we can see new classes of modes. In fact, only last month only, we just talked about these modes, these AKs, as some very generic classes of modes. We have seen there is a universality of flow. Wherever you have vortex dominated flow, we compared two classes of flow. One is flow past a cylinder, a blob body. You know that it sheds Bénard-Karman vortices, so you have coherent structures. And then we also studied flow inside a cavity, and there the lid motion creates a rotary coherent structures. And what we found, that there is a universality of these classes of modes that we have obtained in the external flow and the internal flow. This is something that we can say with some amount of conviction that a new portrait is emerging by using POD in studying nonlinear instabilities. Okay, so what we are now going to do is we are going to talk about another example where vortex induced instability comes into picture. Now, those of you who may have had some exposure of doing some design course in aerospace engineering, so if you have done it, you already know. Those of you who do not know it, let me tell you what is the scenario. That past Second World War, the aircraft speed started increasing, and with the increased speed, you know that you cannot afford to keep the wing as straight. You have to sweep it, and the moment you sweep it, you start getting a different qualitative picture of the flow. It's such a very nice, fascinating tale that of course, during and around Second World War time, there was a resurgence in activities in developing jet engines, and people realized, of course, that you try to go at a very high speed, then you will create a normal wave, shock waves, normal shocks, and that would lead to a huge drag penalty. And it was so huge that people kept talking about sonic barrier, that as if human being will never be able to cross the speed of sound. And then, of course, the engineers are by nature optimists. They don't give up so easily. They kept on studying it, and one of the conference, I think it was in Volta in 30s, where leading aerodynamicists came about, and some of them even suggested that one of the solution is the speed that is normal to the leading edge of the wing. So, if I sweep the wing, then what happens? Although my oncoming flow Mach number could be say 0.7, 0.8, but the normal to the it can be kept say less than 0.4, and then the resultant shocks, those will be created. They will not be normal shock, they would be oblique shock, and they will be weaker. And there is also a possibility which came about much later, that you make the shock absolutely weak, and those are called the supercritical wings. They have come about in 60s and 70s. In fact, these days most of the aircraft that you fly, commercial long distance airliners that you fly, all have this supercritical sections and wings. These are called natural laminar flow wings. We talk about it so casually that it was bound to happen, but in the initial phase it was very, very confusing, because we have noted that for two-dimensional sections, for aerofoil sections, like what you would have in a straight wing, the flow becomes unstable with adverse pressure gradient. But when the wing was swept back, then people noted that the flow transition is occurring over the wing, where actually you have favorable pressure gradient, not adverse. And this was a very, very confusing thing. And time permitting, we will come back and talk about streamwise and cross flow instability of three-dimensional flows past a wing. People have now gotten some understanding of what causes three-dimensional flow to be qualitatively different than two-dimensional flows in showing these instabilities. Concomitant with this story, there was also another interesting story. People found out that sometimes the flow becomes turbulent right from the leading edge of the swept back wing. It was not so for a straight wing. It was only for a swept back wing people noted that the flow becomes turbulent right from the leading edge. And those of you, some of you may be doing a design course. When you calculate the drag estimate for the wing, you assume the flow to be turbulent right from the leading edge for that reason. Because in actual wing design, if you are not very careful, you do not take care, flow actually becomes turbulent right from the leading edge. And this problem is what is called as leading edge contamination. Or we will call it as LEC. As you can note that even in 2004, we have been computing and trying to explain why leading edge contamination take place. So, it was a kind of a puzzle, jigsaw puzzle to aerodynamicists for a long, long time. What is an attachment line first? Let me first show you with the help of a figure, then we can come back. There it is. Suppose you have a swept wing. So, basically we have drawn it in such a way that actual q infinity is the total velocity vector, which has a normal component which is u infinity and a spanwise component along the leading edge, which I call as w infinity. Okay. Now, what happens when I look at the flow field around the leading edge? You actually see that when you have a swept back wing, you have a plane here which is almost like your stagnation point plane. So, that is the attachment line plane. However, flow here is not stagnant. Flow here is not stagnant. What is happening here? The flow actually goes along the leading edge. So, if I am looking at basically, let me just explain to you what we are seeing. We are seeing the following. It is mostly related to aeronautical domain. So, let us talk about it. So, this is your, let us say, the fuselage, and this is your wing. And what is happening here is some kind of a vertical structures are getting created at this corner, and they keep moving along this plane. And in this plane, so in this plane it is like this, where I have shown it. If you project it out of the plane, then that is your attachment line plane, on top of which the flow actually wraps up like this, and on the bottom it rolls down like this. So, it is like a kind of a layer of separation. Okay? Attachment line plane is the layer of separation. So, along that line, what happens? Why the flow becomes turbulent? That is a big mystery. Now, let us go back and give you a kind of a running commentary of what people were looking at, that when you look at the leading edge of a swept back wing in contact with the fuselage, you notice that there is abrupt flow transition, and this was later on studied variously by Ian Paul and Arnold, who noted that this abrupt flow transition is due to convection of continuous turbulent puff along the attachment line plane whenever Reynolds number based on momentum thickness, that is we call this Re theta, is greater than 100, which is equivalent to Re delta star of greater than 245. Okay. These are essentially experimental observations. So, whenever Re theta is greater than 100 or Re delta star is greater than 245, you see the flow becoming contaminated right there. So, how do they do this experiment in the tunnel? It is fairly simple. If you have a tunnel like this, so these are your tunnel walls, then you create a wing, you fix a wing from tunnel wall to tunnel wall. Then what happens? Flow is coming like this. Because of this junction, you will create eddies, corner eddies, and because of the sweep, those eddies are not able to stay there. They are forced to convect this way. That is what they are talking about, that convection of continuous turbulent puffs. Well, you have vortices, but because of the inherently large Reynolds number, they could be quite significantly colorful in terms of spectrum. That is why they are being called as turbulent puffs. Okay. See, while the experimental values of critical Reynolds number are given here as 100 based on momentum thickness or 245 based on displacement thickness, people try to study the flow, study the stability of the flow. How do you study the stability of the flow? In this case also, once again, Prandtl comes to our rescue. Way back in 1946, he has established, we will see it shortly, that the flow in the attachment line plane is essentially two-dimensional. So, here on the attachment line plane, the mean flow, the equilibrium flow is two-dimensional, and if you try to study its instability, then the corresponding critical Reynolds number comes out as 535 if so-called weakly nonlinear theories are invoked. If you do not use weakly nonlinear theory, linear theory gives it a little even higher value. That value, let me just quote to you, it is about 583. That was calculated by Hall, Malik and Paul in 1984. So, we have a linear theory which tells us a critical Reynolds number of 583.1, and if we invoke little bit of weak nonlinearity, we can bring it down to 535, but still it cannot explain the gap between 245 to 535. So, this was considered a kind of a mystery, very much of a mysterious set of affair. Now, let me just tell you that this kind of subcritical phenomena, we thought that we could explore it as a vortex induced instability, because this is a prime candidate, that is what we are talking about. Suppose I have a leading edge of a wing like this, and I have this attachment line plane, and in that plane the vortices are convecting in this way, and this flow is two-dimensional, then it is quite natural for us to investigate this as a vortex induced instability problem. we have the source of vortex as the wing body junction, and we have the flow to be two dimensional, then we have done those experiments that we have seen, that we could, depending on the sign, we could create instabilities. Why don't we explore this? And that led us to this two papers. First, we did some computations in this paper in 2004. That was followed by a detailed study in that JFM paper that I have. Of course, we are once again looking at subcritical instability, right? Because experimental observation is 245, theoretical calculation says 583. So, it has to be a subcritical excitation. So, now this is what we did talk about in this JFM paper, that the flow that rapidly turns to turbulent state right at the leading edge might be due to a vortex induced instability that we have already described, right? We know that boundary layer, attachment line boundary layer is very stable, and this observation that I make here is very crucial. You see, there are two things. In two dimensional flow, we have a stagnation point flow, that the Hemans flow. For Hemans flow, the critical Reynolds number is something like greater than 10,000, whereas zero pressure gradient boundary layer, it is 520. So, there is a factor of 20 involved in 2D flow, but in 3D flow also we see that gap is come down, but still what we can see that that is slightly more stable than your zero pressure gradient boundary layer, because we saw the Hall et al.'s result indicated a critical Reynolds number of 583. So, it is slightly more stable, but here what is being said, it relates to comparing the 2D stagnation point flow versus the zero pressure gradient boundary layer. So, 520 versus greater than 10,000, whereas if I look at the stagnation point flow instability versus attachment line instability, it is not greatly different. It is also greatly different, because for stagnation point flow, two dimensional flow, it is like more than 10,000. For attachment line flow, it is 583. You see, this is one of the reasons that if you are talking about high speed flow, then you will have to keep the wing to have some kind of sweep back. And this kind of phenomena happens, attachment line instability is due to the sweep back itself and due to this corner vortices. This predominantly happens if your sweep angle is more than 20 degrees. So, many a times you will hear people talk about, if we do not have a sweep angle less than 20 degrees, then we have 3D instabilities. So, less than 20 degrees, you have a transition going from 2D stagnation point flow to attachment line flow. Okay? So, this is something that we must remember. Now, Theophilus and his co-authors wrote in 2003 in a JFM paper that till that date there were two major issues that remained unanswered. The first is, of course, related to the phenomena of subcritical instability right in the attachment line plane itself. So, that is the first issue, and this is what we try to do it in this couple of papers. There is also a second issue, that if the flow becomes turbulent at the leading edge, what happens to the flow subsequently over the wing. So, you see, it could so happen that I could have some kind of turbulence set in right here at the leading edge, but that need not go down. So, that is the second issue. Even if the flow becomes turbulent as it goes along, and because it is a sweep back wing, so the streamlines could go like this, and because of various prevalence of favorable adverse pressure gradient, those flow may not be turbulent itself. So, these are the two issues that one did not know in 2003, and at least the first issue of the primary instability was explored by us in these two papers, and that is what we are going to discuss now. Now, people were of course very much mystified for nearly 40 years. You can see that Feininger and Bacon in their 1969 paper conducted experiments, and what they were looking for, that on an attachment line boundary layer, if we can see some kind of instability waves, and they did experimentally noted this. These experiments were subsequently done by Pohl, Arnold et al., then Hall et al., and then Pohl et al. Again, and you can see a continued interest, and it was remaining sort of difficult to sort of explain. In fact, I think it was in one of the early paper by Theophilus in 1993, he made a remark. Tried to compute 2D and 3D flows, and apparently could not see any instability occurring for the two-dimensional flow. So, he made this claim that two-dimensional model equations considered do not deliver subcritical instability of this flow. So, he was trying to write out evolution equation for 2D and 3D disturbance field, and this was in this paper in JFM in 1998. He did that. Subsequently, of course, he teamed up with other people at Göttingen, one of the DLR labs, I think it is in Göttingen, and they tried to study this, and one of his student also did some computational work to see. Basically, it was very interesting. They were trying to mimic our vortex induced instability scenario, and they were not successful. Now, the reason is easy to find out. We will talk about it as we go along when we talk about various efforts gone in there. But one thing that you notice that you do have instability waves experimentally, but no one has established that they will cause transition on the attachment line. We do not have any linear and nonlinear theories that explain this. So, in that context, this was something of a revelation, that that's why this premature transition is referred to as the leading edge contamination. So, as if the flow gets contaminated by some unknown disease, and that was something that remained unknown for quite some time. Now, what we did in this couple of papers, we just posed it as a vortex induced instability, and the free stream convecting vortex in the attachment line plane is being created at the wing body junction. Because this was very much apparent, experienced researchers like Arnold, they have noted this, that the leading edge is contaminated by large turbulent structure coming from the wall at which the wing is fixed. So, if that is so, then it is very, very easy for one to go ahead and do that. In fact, Arnold called this as a bypass mechanism. We also call the same. Gaster even noted very, very early that if you can somehow make these vortices coming from wing body junction become weak, then you won't have such a contamination. And I think he has a patent also, a Gaster's device at the leading edge how to do it. But you know, like these days you can go to the tunnel and you can refine the wing body junction in a much clear way, and you can do that. That is one of the story behind all NLF wings. They spend in designing that wing, in the last stages they do this wing body junction design in a very careful manner, so that your section properties are good, your wing properties are good, but you still should not suffer from leading edge contamination, and that is done experimentally, so that you do not create those large vortices at the wing body junction. Okay. So, as I told you that people had given us enough clue how to go about it. We will show this flow field, etc., but we note that this is another gift given to us by Prandtl, and also in that book by Crabtree et al., that this flow in the attachment line plane is two-dimensional. So, this might help us in studying this. I mentioned to you that there were some computational work done by Schmid's student, Obrist and Schmid. They tried to compute the flow as a vortex induced instability, but they did not succeed for various reasons. We'll talk about that later, but I think one of the main culprits was that they considered it as a three-dimensional phenomena. It is not a two-dimensional phenomenon. That is why they lost it. And the second most important thing they did wrongly was they thought these vortices will move at free stream speed. And now you know through your assignment problem also that you have a very selective basis for C, which is conducive in creating this. So, now we have seen this. Now, let me familiarize you with various coordinate systems that we use in defining the flow. Like here in the lower frame that you see, Q infinity is the total oncoming flow field, which is at an angle alpha to the normal to the plate. So, you could get a U infinity and a W infinity. Now, in this analysis that we are going to talk about, we are going to talk about as if this wing is infinitely swept. Infinitely swept means that it is a never ending wing on this side. Okay? So, there are no such wing tip effects involved, and that is not too bad actually. You can see the equilibrium flow itself creates a bias of the flow going from this side to that side, and even if you prematurely terminate this, you are fixing this wall to wall. That is one of the way of doing a 2D experiment, but in this case also you will see a vortex getting trapped, created here, and that can wash out downstream, but it cannot propagate in this direction, right. So, that is why if you look at these experiments, they are very trustworthy and reliable, simply for the reason that the vertical structure that is getting created on the other wall will not propagate against the sweep. Instead, the vertical structure that is going to be created here, they will naturally move along, right. So, that is your attachment line plane, the way we have shown here. It is extending towards you, and then in that flow what you notice that there is this wall streamline. You can talk about a streamline which is indicative of the flow direction on the wall, and then once you move out of the shear layer also, you get another streamline that we call as external streamline. So, these two lines are not same. Okay. In addition, then we have a wing fixed coordinate system. So, there is this wing fixed coordinate system. This capital X is normal to the leading edge and capital Z is along the leading edge. So, that is that, and Y is perpendicular. So, that is your wing fixed coordinate system. Then we have here external free streamline based coordinate system. So, we show its projection on the wing itself. So, we project this on the wing itself, that is along this, So, there we draw a tangent, that is our x1 axis, then we have perpendicular to it is a z1 axis, and y1 or that is also the y is fixed on the normal to the plane. Okay. So, these are the various coordinate systems that we should be talking about. So, please keep this in mind that we would be looking at this. I will pass on this slides to you for you to take a look at it carefully. So, basically once again we note that Jan Paul has done this experiment, and he showed there is existence of attachment line vertical structures. What he did, of course, he did a interesting thing. He did not do it with the wing section. He did it initially with a cylinder called a yacht cylinder. Usually when you do the experiment, you have a cylinder which is perfectly normal to the oncoming flow. So, he just swept it. So, he did those experiments, and that is why we are going to study it at a subcritical instability by looking at the role of convecting vertical structure in explaining leading edge contamination from the solution of two-dimensional Navier-Stokes equation in the attachment line plane. The attachment line plane will suffer similar to vortex induced instability problem. So, we have stated it time and again. Okay. What we do here is basically again we take a two-dimensional plane. So, the computational geometry is going to be exactly the same that we have done it for the earlier cases. So, what we are going to basically study is a domain like this. So, this is our wing now. Now, there is no question of taking leading edge, etc. So, we take a box like this. That is your attachment line plane, and then you have vortices migrating outside the shear layer. And what we did is basically we did take about equispaced 501 points in the streamwise direction, and normal to this wall we have taken stretched grid like this. So, this side we had 501 points, this side taken 101 points. Okay. And some results we will see shortly will be for the case of a counterclockwise circulating vortex convecting at a speed of 0.20 and at a height of 30 delta star. So, basically we purposely took it little more than what we had done in the previous experimental case to show that even this attachment line profile has a little higher receptivity, because we are keeping the vortex little farther away. Okay. So, as compared to zero pressure gradient boundary layer, we have purposely taken this height to be a little more. Okay. So, this is what you see. This is what you see as the instability on the attachment line. At earlier times, you can see again this bulge in the shear layer, which actually degenerates into erupting vertical structure at later time, and this is what is noted as the vortex vorticity contours due to a counterclockwise vortex. Now, in fact, if you look at the first frame, the top frame, that corresponds to a time when the convecting vortex is outside the computational domain. So, even there, when it was out of the computational domain, its influence is clearly seen here. You can, as I said, that was that. The second frame, that is at t equal to 748, the convecting vortex appears over the computational domain, and the intense sequence of instabilities are seen. And if we look at a large time, the convecting vortex is located at the x equal to 460, while the leading edge of the coherent structures, they have actually moved out of the computational domain. Okay. Now, the shear layer that is aft of the convecting vortex is always stabilized, because that introduces a kind of a favorable pressure gradient, right, that we have talked about. And you can see the shear layer would thin down there in those regions. That you can see actually in those later frames. If you if I show it again, you will notice that in these cases you can very clearly see that vertical events are taking place here, but the shear layer is thinning down as you are going down. This side you have a thicker boundary layer, this side you have a thinner boundary layer. So, these are some of the things that shows one-to-one correspondence between this equilibrium flow versus the Blasius flow that we have studied. Okay. Now, we did show a case in this paper, gamma by V about this kind of value. See, this is trying to make it a kind of a non-dimensional core size of vortex as this. So, basically what it is, you can see that again these are finite core vortices, these are viscous vortices, those are going, and the non-dimensional core size is okay, and the first bubble occurs at a location where the Reynolds number is basically about 190 based on delta star. Okay. If the appearance of the first bubble is considered as indication of flow criticality, then this is indeed a case of subcritical instability that we are trying to establish. Okay. Oh, I think I should stop here.